Welcome. This is a Powerside technical video, and I'm your host, Chris Duffey. In this video, we're going to discuss short circuit analysis and how it's relevant to you. All right, let's move on to some slides. And what I'd like to do is start with some introduction and history. It always seems to be a good place to start when we're talking about topics like this. And from the onset of electrical power systems, there's been a need to remove short circuit conditions from electrical systems. Even the best planned systems can incur short circuits. And short circuits lead to outages, loss of production, they jeopardize safety. And well-designed systems will help us to remove those short circuit conditions to limit equipment damage, reduce fire hazard, and to prevent injury. Now, as I like to do in these videos, I like to bring up certain pivotal engineers, and that person for me would be Conrad St. Pierre. Conrad was one of the most knowledgeable industrial power system engineers of the last 50 years. His extensive volumes of engineering data and technical articles have been shared liberally with many of us. I've benefited greatly from his expertise and then also the data that he's supplied to me. He worked at GE Switchgear and IPSIO, the Industrial Power System Engineering Operations Group at GE, and he became the head of IPSIO in 1986. When I met Conrad, he had changed jobs, come over to Power Technologies, Inc., where we met. I was working at PTI at the same time. And then after that, he became his own consulting engineer, working out of his house in Rotterdam, New York. Conrad was versed in all areas of electrical network simulations with a specialty in short circuit and protection coordination. And he wrote a detailed text, and I'd like to show it to you, on calculating short circuit currents. It's called A Practical Guide to Short Circuit Calculations. And if you want to know more about short circuit, I suggest you get a copy of this book and you read it. It's pretty filled, and as you can see, it's rather thick. So Conrad definitely put a lot of material in here for us to benefit from later after he was gone. And I do appreciate that. His text also includes several notes on Walter Huning, who was also a pivotal engineer. He was at GE. He developed several of the ANSI short circuit methods that are used in calculating fault currents. So thank you, Conrad. When short circuits happen, they're typically of two forms. One is self-initiated and the other is forced. So self-initiated would be those type of faults that are caused by insulation failure. Now, whether that's from dielectric breakdown or for thermal damage or aging of the equipment, that would cause a self-initiated fault condition. A forced condition would be one that is external. One typically due to animals, trees and debris in a storm, or construction equipment digging or hitting an overhead line. And in either case, an arc is usually instantiated. At the point of the fault, you can get burning of conductors, and for many cases, an arc blast condition, which is considered in arc flash analysis. So it seems we have a pretty clear need to know how high the current is if we want to really understand its implications of what's happening. And those of you familiar with arc flash, you certainly know that the incident energy is directly related to how high the fault current is. So we have a need. We have a need for short circuit analysis. Now, the key figure of merit that we're going to be determining from this analysis is the fault current magnitude. And this value is critical when applying equipment to serve loads. Equipment must withstand both mechanical forces and the heat generated during these high current conditions. The fault interrupting devices must remove the fault safely and without damage. And in addition, those same devices must be rated according to their fault interrupting capability so we can apply them. That magnitude of fault current also helps optimize protective devices for device settings to help us to curtail fault conditions as quickly as possible while removing the least amount of equipment from service as possible. This is a balance. This helps us balance the selectivity versus protection so that we can achieve the least amount of process interruption. That helps us to maintain profits while at the same time endeavoring to minimize damage, which saves on repair costs. So we want to optimize our system as best as possible, and having fault current magnitudes for protection coordination helps us do that. And also, as I just noted, fault current magnitude is used as the input, the key input result when performing arc flash computations. Now, one other key value that is of importance is the equivalent fault impedance X over R ratio at the point of the fault. This value is used for additional calculations that help us determine the total fault current from AC system effects. And in particular, we need it for the DC offset, which we're going to discuss in just a few slides. So historically, we moved from manual calculations by hand to DC network analyzers to analog network analyzers, and finally in the 1960s to digital computers, which is where we have most of our experience. But before the advent of digital computers, Charles Fortescue developed symmetrical component analysis in 1913 for analyzing unbalanced three-phase systems. And after its adoption in 1937, it became the de facto tool for calculating unbalanced faults. And I would say today that is still true. I mean, sequence component analysis is everywhere throughout fault calculations, and even in power flow solutions, and now even in dynamic stability. It's slowly moving into there, which is still predominantly positive sequence. But then, of course, in the transient simulations, if you want to look at results and see what their sequence component results and their answers are, you still have to process that data. So these are the three key items on this slide: development of symmetrical components, the advent of digital computers, and those digital computer breakthroughs which were performed by William F. Tenney of Bonneville Power. He made the greatest advances in digital network computations involving matrices and the admittance matrix in 1967. I have more commentary on this, by the way, in my power flow video if you want to read more, listen to more about William F. Tenney at BPA. Now, Tenney's methods directly affected short circuit analysis. His sparse matrix methods greatly enhanced the speed of short circuit calculations. Optimal ordering, partial refactorization, a fast forward, and a fast back. These four methodologies basically sped and supercharged short circuit analysis, especially when they're blended with Thevenin's theorem and sequence component methods. When done that way, these allowed for extreme speed. So let's have a little bit more detail on this. So in Tenney's methods, if you wanted to fault an entire system quickly, you build, order, and factorize your matrix, both positive and zero sequence. And then at the fault bus, all you need to do is perform a current injection. And when you inject the currents and then solve using fast forward and fast back, then you achieve you'll get the voltage in your result, but since you inject a 1 per unit current, it actually gives you the positive and zero sequence impedance at the point of the fault. If you then assume the negative is equal to the positive and then connect those impedances appropriately, then you can calculate any form of fault, whether it's line to ground, line to line, double line to ground. And in particular, one of them, line to ground fault, you take Z, positive, negative, and zero, you put them all in series so that you can calculate what the impact is from a fault current that is line to ground. Now, if you want contingency analysis on top of that, for line outages or open and closed breakers or just a series of network changes, all you have to do is perform a partial refactorization after the equipment status change and then redo points 2, 3, 4, and 5. So rinse and repeat, rinse and repeat. You could just systematically perform hundreds of thousands of short circuit computations in a very short period of time with these methods. And by the way, just of interest, the ordering method. If you leave out optimal ordering and you have a large network, 5, 10, 15,000 buses, you can find your computation time exponentially increasing. I did this one time. I had a 13,000 bus system, and when I left out optimal ordering, this was 15 years ago, computers were a little bit slower at that time, a power flow solution would take place in about 5 seconds. Without optimal ordering, that solution was not complete after 8 hours. And so these were dramatic improvements to help us speed our computations. Now, for these admittance matrix methods, we now see that they've been supercharged with all these advances that came about. However, they have one shortcoming. They only supply symmetrical fault currents. And this is only one part of an AC fault. Due to the behavior of the AC system with reactance, resistance, and rotating equipment, we find we need to know more. And in fact, 3 key things are involved in an AC fault, and that would be the symmetrical current result, the DC decay, and the AC decay as shown here in this figure. So if you have remote sources that are far away from you, and you have no motors and no generators that are near you, and you have a fault condition, that current will appear and then stay constant throughout the fault, and that is this blue curve here. If during that fault, and when you apply the fault, when you hit it point on wave, not at a zero cross of the voltage waveform, at anywhere else, you will find that the current will offset itself. And so you get a DC offset in the current that then decays based on the X over R ratio, and that's the orange line here. Okay? And last is the AC decay. So if you have any nearby sources, if you have motors or generators that are nearby, what you'll find is there's an AC component, a fault current contribution, that will decay over time due to the time constants in the rotors of those machines. And so when you add all 3 of these together, and that's what's done here, all 3 of these on the top are added together and they produce the current that's on the bottom. So you can see the total fault current has a DC offset, it has a DC decay, it has a high AC component, and then it has AC decay, and it finally settles into what's left over at the end when everything decays, which is the symmetrical current. The symmetrical current is what we calculate using all of the admittance matrices methods. All right, that leads to this table, and let's not go through the whole thing. Let's jump down to row 3, which is using the admittance matrix. We'll find that when we get done, we still need to take the X over R and do additional lookup onto tables or curves or equations to get what the total fault current is using the X over R ratio. If you use a power system dynamic simulation and the machine dynamics are modeled, if they're included, the AC decay will be included in the simulation. So you don't need to calculate it in an extra fashion. All you need to calculate is the DC decay component using the X over R ratio at the point of the fault. If you're performing a transient simulation, which has all the transient detail of the impedances, of the machines, all the machine dynamics, then you'll find it's all included in the simulation and you don't have to do anything at that point, but just take the current and analyze it for its values. Okay, so that's our introduction in history. And to bring relevance to short circuit analysis, I'd like to provide helpful notes, and that is, in every discipline of engineering, electrical, mechanical, all of them, we find that we have helpful rules of thumb. And short circuit basically has an overabundance of these. So I want to look at these and consider the following helpful notes as they relate to a number of network components and how short circuit currents are calculated. And hopefully, these will bring greater relevance to the AC equipment involved and their data. So if you're a manager, you'll look at, or you'll be listening to engineers in a meeting, and you'll say, okay, they're talking about all this stuff that they need for this computation, the software they need. Why is all this, is this really relevant? Is it really needed? And so hopefully by going through some of these things, you'll see some of the key values that are necessary for short circuit computations. Okay, let's start with the first one. Motor times locked rotor current and the per unit locked rotor impedance of a motor are inversely related. And you can see that here with the equation. So for example, if the times locked rotor current is 5 times the full load rated amps of a motor, then the locked rotor impedance is 1 over that value of 5, the 5 times value. So X locked rotor would be 0.2 per unit. Likewise, the initial instantaneous symmetrical 3-phase fault current contribution from a motor is the times locked rotor current times the motor full load amps. So if you have the times locked rotor, you can multiply it times the FLA and you will achieve and get the initial before it decays fault current contribution from the motor. And that's shown here as I locked rotor is 5 times, full load amps is 500 amps, 5 times 500 gives you 2500. Now on a transformer, when you fault the secondary of a transformer and it's fed by a strong upstream system, then the fault current is equal to the rated transformer amps divided by the nameplate per unit impedance, Z. For example, if a 1500 kVA transformer is rated 1800 amps at 480 volts and has a 5% impedance, the symmetrical 3-phase fault current should never be greater than 1804 divided by 0.05, which is the per unit impedance, and that equals 36,000 amps or 36 kiloamps. Now, for a generator, for faulting right on the terminals of the generator, the 3-phase fault current contribution is, in a similar way, the rated generator amps divided by a quantity called X double prime D. Now, yeah, there's a difference between saturated and unsaturated values, but let's just look at this just from this perspective of X double prime D. You should, for the worst case fault current, you'd use the saturated value, but either value will get you close. If a 1500 kVA diesel generator is rated 1800 amps at 480 volt and has X double prime D as 10%, then the symmetrical 3-phase fault contribution from the generator should never be greater than 1804 divided by 0.1, which is 18,000 amps. Now, of course, this will decay over time, whereas if this had a stiff source for the transformer, right, it's going to stay there as a symmetrical current value and it's not going to change. But if there's a generator, that current will decay over time. Here's a few more individual items that are worth noting. Notes on each one of these lines. X over R ratio of transformers typically increases with MVA rating. If you want to see more details, look in the red book. There is a table that shows typical X over R ratio versus MVA. The typical impedance of a 3-phase medium voltage low voltage transformer is about 5.75%. The typical impedance of a 3-phase utility substation transformer is about 9%. X double prime D of a generator varies between 8 and 25%, and a typical induction motor has a rating of about 1 kVA for 1 horsepower of rating. A line to ground fault on a secondary or on the secondary of a delta Y transformer appears as a line-to-line fault on the transformer primary. Seems important then to know what the winding configuration is. Given Z and the X over R ratio, this is for transformers mostly, you can calculate the individual values of R and X by using these equations. Distribution feeders have a typical reactance between 0.5 and 1 ohm per mile, and greater conductor spacing on an overhead line leads to higher reactance. Evaluating remote voltages for fault conditions. helps with understanding voltage impact, or sag depth during a fault. So that means short circuit computations can help with evaluating sag impact. Induction motor fault contributions die away quickly, within less than 0.2 seconds. The curve shown here at the bottom of the slide is a 5,000 horsepower motor that's faulted on its terminals, and you can see very, very quickly, the fault current goes from its maximum locked rotor value, right up here. This is that maximum locked rotor value we talked about, but it decays very, very quickly over time. And this is why in the ANSI standard, it's important to consider the AC decay when calculating interrupting current for your protective device duty, because this current decays very quickly, and that's included within the ANSI standard. And there's a lot more, but hopefully this illustrates the relationship between impedance and short circuit current, so it can show you the importance of the equipment impedance data and how relevant it is to short circuit computations. Now, let's even step further with relevance, and that what is it going to give us? What are we going to get out of a short circuit analysis, or what additional computations can be performed with the results of a short circuit analysis? First, again, let's note what the key metrics are. The key values coming out of short circuit analysis are the fault current magnitude and the X/R ratio at the point of the fault. But in addition, if we perform a fault and we calculate the rest of the network conditions, we'll also be able to obtain the upstream currents and the remote voltages. Again, remote voltages help you determine sag impact, and the remote upstream currents help you know upstream devices, how fast they're going to trip versus downstream. And that's important for arc flash analysis, determining which devices are tripping first. So from these results, a host of relevant engineering analyses can be performed. Equipment duty, the first most common one, and that is we take our fault currents, we adjust them appropriately, and we get a duty which is then compared against protective equipment ratings, fuses, breakers, and switches. Next is protection coordination. Fault currents are the foundational element used to determine protective device settings and to estimate trip times. You can't estimate trip times unless you do it at a particular fault current condition. Arc flash, as I just noted, the fault currents are used to calculate the incident energy, which is reported on arc flash labels and arc flash work permits for worker safety. So without the fault currents, you cannot perform arc flash computations. Voltage sensitivity. I mentioned this earlier also in regards to voltage sags, and that is if you have a software that will calculate not only the conditions at the fault, which is the fault current magnitude, but also remote conditions in your network, then you can see those remote voltages and determine the sag impact on your system. It helps in understanding the plant and the system-wide impact from faults. Equipment overstress and overheating. Fault currents produce mechanical and thermal impacts, all right? In addition, right, to the impacts on breaker switches and fuses. And in particular, transformers have defined through-fault protection curves, and cables also have thermal damage curves. So from fault currents, we can then compare these, the fault currents against what the damage curve says, and if we interrupt that fault current soon enough, then we won't cross into the damage area of the curve and will prevent damage on our transformers and cables and other equipment that also have damage curves. The system strength. So fault MVA, which is calculated by multiplying the current times the rated voltage times √3, supplies critical information for evaluating voltage compensation equipment stability. So what I'm talking about here is like a StatCom that's on your system, and it's in a voltage feedback mode, and its control systems are looking at seeing how the voltage changes with how much current it puts out into the system. The weaker the system, which means the lower the fault MVA, the more difficulty they'll have in keeping that stable and within its control parameters. So knowing the fault MVA helps with that. And finally, one of the probably the most key items I would say in terms of how this impacts other analyses is how the calculated system short circuit Thevenin equivalence can be used in voltage impact analysis for high current loads like motor starts, other impacting loads, other short circuit calculations and studies, right? When you perform a study, the utility will not give you their whole network model. Nope, they'll give you a Thevenin equivalent. Well, they get that Thevenin equivalent by performing a short circuit analysis. Harmonic distortion and evaluations, harmonic distortion evaluations and compliance evaluations. Harmonic analyses need an upstream short circuit strength. I would prefer that to be a complete harmonic equivalent, but you at least have to start somewhere. So a short circuit equivalent is a good place to start. And dynamic and transient simulations also rely on upstream equivalents so that they can perform their simulations without having to modeling the full detail of everything that is upstream. So equivalents are very important, and calculating that Thevenin equivalent from a short circuit analysis gives you that information. All right, so I'm sure you noticed, and I said this in my other videos, that Powerside is a power quality company. So why am I even talking about short circuit? Well, in the same way that a model simulates reality, in the same way that a model simulation relates to an actual system condition, PQ and short circuit are a natural reality simulation pair. Let me say that again. In the same way that a model simulation relates to an actual system condition, power quality and short circuit are a natural reality simulation pair. For instance, power quality measurements can supply benchmarks for short circuit model validation. If you've captured a power quality event and you know where you are in the system, then you can, in your model building, you could use that as validation in that you actually calculated the right number in your model. Power quality measurements capture conditions that need to be understood so models can be improved to predict them. So we want to use our predictive nature of our models here, but how do we make sure the model is good enough? Well, we capture those conditions and then we can improve our model. Short circuit simulations predict expected power quality conditions for design and system operation. Yes, especially on voltage sags, which we just mentioned, and fault current magnitudes, if we're capturing those power quality events as well. Both simulated fault currents or high current events and remote voltages, voltage sags, are completely and immediately useful, right? In comparing short circuit model results versus power quality captures. Short circuit simulations can show why poor power quality exists. If you look at remote voltages and you see that your sag went down below 70% on this other bus, you can expect that you have a fault there, that your motor contactors are going to trip on that other bus, right? Short circuit simulations can be used to specify equipment that improves power quality. So you build your network model, you put a fault on the system, you realize you have a voltage problem. Now you take this and you perform an alternate switching configuration to stiffen the system, and what happens? The voltage goes higher at that remote location because you stiffened the grid for that fault condition, or for where the fault is going to be located on that other alternate network. So you can see how you can improve power quality by performing an analysis. Now, short circuit simulations, this is really key and pivotal. Short circuit simulations have a network view that can aid power quality measurements which have a narrow field of view. So as a pair, remember the reality simulation pair, as a pair they bring greater depth and understanding to many power quality conditions where you're basically blending modeling or digital twinning with actual measurements. And in general, overall, short circuit simulations and power quality measurements can be used to validate each other. All right, that pretty much wraps up this video on short circuit. And just a couple concluding slides. Our hope is that you have a greater appreciation for short circuit analysis and all that goes into it, and that you'll make greater use of it for your modeling and simulations and for for work that's necessary on your own system, so that your engineering designs and analyses are greatly improved and with a firm engineering foundation. And now at Powerside, we're keenly aware of the importance of short circuit analysis, as we are with power flow and stability, motor starting, and many other analyses that can be performed. And in particular, we use short circuit analysis to properly engineer our designs, aid in the interpretation of power quality conditions, and speed our workflow. So that pretty much wraps up this presentation. And thank you very much for listening. And I hope this was really useful to you. Obviously, if you have some questions, additional questions about things regarding to short circuit analysis and computations, you can get a hold of our sales teams, and they'll reach out to us at engineering, and we will do our best to help you out. So remember, in addition to this information, you as a person, as an engineer, we really hope that you can be the best engineer that you can be, and that this will be helpful to you. Thank you.